In this example, we're given a circuit diagram that contains 1, 2, 3, 4, 5 resistors and a voltage source. We're also given the value of one of the currents flowing through one of these resistors, I0, and we were told that it's 1 amp. And we're asked to find this particular one, I1, and also the power associated with all of the circuit elements. Figuring out the power associated with all the elements means we have to figure out all the voltages and current throughout the circuit. So let me just summarize all the currents and voltages that we know across the circuits. And the first thing we need to do is we need to put some assumptions, because while I know the directions of I0 and I1, I don't know any of the other currents or the assumptions about the voltages. So typically we go ahead and just assume certain voltages and currents and we name them. So I'll start by saying, well, I'm going to put that here and that here as a voltage drop across the 50 ohms. And then we have across the 4 ohms, I'll put this is plus, this is minus. Of course, I'll also have to specify or assume certain current. I don't know it ahead of time, so I'll have to assume it. And then based on the number we get, if it's negative, it's just our assumption is wrong. And I'm going to assume that the current is going through this. And if you have the freedom to figure out the directions of the voltage or the current, I recommend that if you're assuming the voltage and the current that way, that the current is going to the positive side, so that you don't have to use the negative of the passive sign convention. It just makes your life a little bit easier. I mean, you don't have to, you can just use it the opposite way, but I just find it a little bit easier. And also this one here, I'm going to assume that the current I10 is coming from here. I'm going to call it I10 for 10 ohm. And I also will assume that the voltage drop across it is this way. Of course, we can call it V10, V4, and so forth. So for example, I'm just going to call this here as a V4. This one here is a V10. And how about this one here? Between this and that, I'm just going to assume that this is I25. And I'm going to also call this as V25. This one here is named for us as I1, so I will just assume that this is plus, this is minus. You can call it V1 or V65. I'll just call it V65. And what else do we need to know? Well, the direction of the current going through this one here, IS. I could have just simply done it the opposite way, but I'm just going to do that because it's a source. I mean, you don't have to. You can assume that IS is here and just assume that when you use passive sign convention, when we compute the power, you just multiply by plus. Do we have anything else? Probably I should put this as V50s for 50 ohm, or you can use I0 since we have called this I0. It's up to you. Naming doesn't matter. All right, so let's list what we know and what we don't know. So I will list all the circuit variables that we have, and we'll figure out what we know and what we don't know. So first, I'll focus on the resistors. So we have the V50 for the resistor, and we have, of course, the I0, and I0 is 1 amp, so I know that already. And we have the 4 ohms, so it gives me the V4, and I also have I4, and we have the V10 for the 10 ohms, and I have I10, and we have the V65, and we call it I1, the current associated with it, and then we have V25, and we have I25, and of course we have the voltage source. I'm going to call it VS. I don't believe I called it anything in here, but we can just simply say it's VS. So it's VS. Let me just write it in here. So this is VS. And of course, the current associated with it is IS. And I know that this is 150 volts. Okay. All right. So let me just highlight what we don't know. So we don't know this, that, and this we don't know. We also don't know the V25, for example, or the V65, or the V10, or the V4, or the V50. However, we know because these V's in here are associated with Ohm's law. So if I know the I4, in here, I will definitely know the V4. If I know the I10, I'll definitely know V10, and so forth. So technically, I kind of know these. And frankly speaking, I already know the V50 because I know what the I0 is. It's simply 50 volts because it's going to be 1 times 50. That's what it will be. Passive sign convention is positive, so I can just go ahead and write it here. That's simply 50 volts. That's what it is. So this is not an unknown for me, at least, because I was given I0. All right, so what's left? Well, what's left is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 unknowns. What I really need is 9 equations, but I know out of these 9s, I know that these 4, Ohm's law will give me that. So technically, I should focus just on the red, which is 1, 2, 3, 4, and 5. So I need to write 5 different equations in order for me to be able to solve this circuit and figure out all the voltages and the currents. And these will come from KCL and KVL. So I'll start by identifying, I'll start by writing the KCL equation. So for KCL, what we need first is to identify certain nodes. So I have dedicated these nodes here on the circuit. Effectively, you have 1, 2, 3, and 4 nodes. And well, in KCL, if you identify that these are all the nodes throughout the circuits, technically out of 4 nodes, we can get 4 minus 1, which is like 1 is always, you can figure out the last equation. It gives me 4 equations, and the fourth one is always dependent on the other 3. So only the independent are 3. So you need to identify different equations to write, or different nodes to identify the KCL for. So let me just say, well, I will focus on this node, and this node. I could have picked up any 3 nodes. What I'm saying is, like, let's write 3 KCL equations using 3 of the nodes, because the fourth node, the equation coming from the fourth node can be, or is dependent on the other one, so it's not very useful. Of course, you can use any 3 combinations. However, I made sure to use this node and this node because it has I0 associated with it, so there is a known coming in and out of it, which makes my life a little bit easier. But if you chose this node or this node, it's pretty much the same. But I just chose these, so I'll write 3 KCL equations. That will give me 3 equations. So let me just write this in here. So that will give me 3 equations. Okay, but how many do I really need? Back to these numbers: 1, 2, 3, 4, and 5. So 3 equations came from KCL. That means I need from KVL. Let me just do this here. I need 2 equations from KVL. So 2 equations in here. You can write more equations from KVL and less of KCL, but I find it a little bit easier to do this analysis this way. It's not a strict way, it's just the way I think about it without having any knowledge of the more advanced circuit analysis techniques, which we'll go through it in different or later concepts. There's more structured way of figuring out all of these. But for now, I know that I need to write 1, 2, 3, 4, 5 equations. So I'm going to use 3 from KCL and 2 from KVL. And of course, for the KVL, I need to identify some loops. So I'll assume maybe this is the first loop. You can pick up any 2 loops. It doesn't matter. I just decided to do this loop, and of course, I will use one that is basically the outer loop in here, and I'll write 2 equations. All right, so let's go ahead and write the KCL equations at the different nodes. I'll call this node as A, B, and C. Okay, so I'll basically go ahead and just write the A node here at A. What we have is the following. At KCL at A, we have 3 current, 2 leaving, and 1 IS is coming into the node, and we have I4, and we have the I0 plus 1 amp leaving. This is the KCL at A. What about B? Well, at B, we can just say, well, I4 is equal to I1 plus I10. Okay, what about at C? Well, at C, we have the 0. Let me just make sure that you see this one here. This is the I0, this is the I10, and the I25. So I25 is simply I10 plus 1. Again, I want to re-emphasize that the use of C and A will make the life a little bit easier because we can use these ones in here. All right, so I wrote the 3 equations for KCL. Let's write the KVL equations. So the KVL equations, I'll start with loop 1. I'm just going to write it in here. This is loop 1. Okay, for loop 1, it will be V4 plus V65 minus 150 volts equals 0. So that basically, I said plus V4 and then plus V65 and then negative 150. That's where this negative came from, and they're equal to 0. Let's write the same thing for loop number 2. Loop number 2, we're going to go from here. So that becomes this one here, for example, plus V50, and then we come in here. Of course, this doesn't matter, this doesn't matter, this doesn't matter because they're not part of the loop. All right, so we will do that. That will be V50 plus V25 minus 150 equals 0. Again, so we went in here just to double check. We went from here, and then here, and then here. So we have 5 equations, and we have 5 unknowns that we're looking for the currents, 1, 2, 3, 4, 5. But the KVL equations are written in terms of voltages. So what I need to do is I need to use Ohm's law to convert these voltages into currents, and I rearrange the circuits and rearrange all the currents. So let me just do this. All right, so what is V4? Well, again, V4 is just simply 4 times I4, and you can write these Ohm's law in here. So we can write them for all the different equations. So you can say, well, V4 is simply 4 times I4, and I10 is simply 10 times I10, and the V65 is simply 65 times I1, and then the V25 is simply 25 times I25. And again, just to reemphasize, because I assume that all these currents are hitting the like this current is hitting the positive, this current is hitting the positive, this current is hitting the positive, and this current is hitting the positive, and this current, if I wanted to use it hitting the positive, it just makes my life a little bit easier when I'm writing Ohm's law. Okay, so we rearrange all of these. So I will rewrite this equation. So equation number 2, I'll just rewrite this equation in here. So let me just do that. So it's a rewrite. I'm just going to call it the prime. So V4 is just simply 4I4 plus the 65 is just simply 65I1. And we have negative 150 equals 0. And what about the V50? Well, the V50 is actually 50 ohm. We already know what V50 is because we computed it already. So we can just say V50 is just simply, this is the 2. That V50 is just simply 50 ohm plus V25. Where is the V25? It's actually here. And of course, we can take a look in here as well. It's 25 times I25. Okay, 25I25 minus 150 equals 0. So now taking a look, I'm just going to highlight, I have 1, 2, 3, 4, and 5 equations. All I have to do is just solve them to figure out all the currents throughout the circuit. And you can use any technique you want. For example, substitution might work in here. For example, the I25 is isolated in here, so I can figure out what I25 is. And I substitute it somewhere here, for example, and by substituting it, I will know what I10 is. And by knowing I10, I can substitute it anywhere else. So for example, I can substitute it in here and so forth. And you can go ahead and do that, or you can use Kramer's method. You just rearrange these currents and voltages in a matrix and use Kramer's method with the software and figure out all the I's that you need. So solving the equations will give us these particular current values. So we'll see that I4 is 5, I10 is 3 amps, I1 is 2 amps, and I25 is 4 amps, and IS is 6 amps. So we technically have everything we need. Of course, I didn't compute the V4, but it's straightforward implementation of 4 times 5, that's 20. Well, 10 times 3 is 30, 65 times 2, that's maybe 130 volts, and then 25 times 4 is 100 volts, and so forth. So we can figure out the V's based on the I's. So we have everything we need. We were asked to figure out what I1 is. Well, it's straightforward. It's a 2 amp. Okay, so we have that. Now, what we need to do is also figure out the power associated with each circuit element. So of course, we can use the definition of the power, which is simply P equals I times V for any elements throughout the circuit, of course, plus minus based on the passive sign convention. Or for resistors, which form the bulk of the circuit, we can compute P equals I squared divided by R, or I squared R, sorry, R squared R, or V squared divided by R, or of course I times V. It's up to you to use whichever method you want. I'll probably use, since I know the currents already here, I just use I squared R to compute them. So I'll just go ahead and compute all the powers associated with each one of them. So first I'll start with the source because it's a little bit different. So P of the source, which is 150. Of course, the source is 150 volts, and I know that current is 6, and I know that it's hitting the negative. So it's simply negative I times V, which is negative 6, times V, which is 150, and that is basically that's basically the source of all the power generated in the circuit, because this is the only source that we have, which is 900 watts. That's negative, and of course it is generating power because of the sign is negative. All right, we can compute the different powers. For example, the P for the 4 ohms is simply I squared times R, which is 5 squared times R, which is 4. Okay, so that basically makes it 100 watts. And so forth. So I went ahead and computed the rest of the powers. And these are here. You can pause it and just double check that your answers are correct. And if you sum all these powers, you'll see that, of course, the resistors are consuming power, and the sum of that power that is consumed should be equal to the sum of to the power that is being generated. So these will be 900 watts, and this is negative 900 watts. And if you sum them, they'll sum up to 0.